So we saw composite functions pop up when we did inverse trigonometric expressions. So we played a little bit with these in our class, but I want to make sure we can bring it back to just general function notation as well. So our composite functions is when we layer a function within another function. So it's that we have this input that creates an output for g of x, and that output for g of x becomes the input for f. So what we want to do is make sure that we work from the inside out when we deal with these. So if we have these two functions here, f and g, and I want to evaluate f of g of 4, you can do this a few different ways. You could keep it all together, meaning what I could do is have f of, and then big parentheses, and inside of there, evaluate g of 4. You can also just evaluate g of 4 off to the side. That's perfectly fine. Sometimes that can lead to forgetting that you need to plug it into f at the end. So I'm going to keep it all together in this single notation, but just know that you could do side work to evaluate g of 4 separately first if you wanted to. So g of 4 means I have an input of 4 and I'm going to my function g of x. So what I want to do is evaluate, so g of x says take 1 divided by the square root of, and then what we're taking the square root of is positive 4. So this is the same thing as f of 1 over the square root of 4, which is equal to 2. So I'm taking that 1/2, and now I'm plugging it into my function f of x. So f of x tells me to square over square minus 2, and our square is going to be of 1/2. So this will be a 1/4 over 1/4 minus 2, which is 1/4 over, and if it helps we could think of that as 8 over 4, so equivalent to 2, but we have our common denominator, so that's a negative 7 over 4. And there's a few ways you could rearrange this, but you could use the what we did in that previous video of multiplying both the numerator and denominator by the least common denominator, which would be that denominator 4. So in that numerator, that would just cancel out and leave us with a 1 over, and in the denominator the 4's would cancel and we would just have a negative 7. You could also think of it as 1/4 divided by negative 7/4, which is we keep, change, flip. So we keep our first piece, change to multiplication, flip the second piece, and those 4's would cancel out, so then you would see your negative 1/7 there as well. So either way works. Alright, f of g of x. So if we're not plugging in a number and we're just working with our variable of x, then what this would look like is f of, and we just copy g of x from up above there. So that 1 over square root of x. And then what we're doing is we're taking all that notation and plugging into f, which tells us to square over square minus 2, and we have a 1 over root x, 1 over root x. So 1 over root x squared would just be a 1 over x over 1 over x minus 2. Again, I don't want to have a complex number, so I'm going to multiply the numerator and denominator by the least common denominator, which is this kind of shared value of x. So I'm going to multiply by x, multiply by x. In the numerator, those will cancel out, so we'll just have a 1 left over. In the denominator, we'll need to distribute. So x times 1 over x will just leave us with a 1 minus 2 times x, so a 2x. Now I see if I can do anything else with that, but that's going to be pretty much stuck like that. Alright, what if we switch it around? G of f of 1. So what this will do is we'll have g of on the outside, and then f of 1, so f tells us to square over square minus 2, and what we're plugging in is the number 1. So this will be g of 1 squared over, let's see, 1 minus 2, which is a negative 1. So here we're just taking g of negative 1. Now g tells us to take 1 over the square root of the input, which we're plugging in negative 1, And we are ending up with a square root of a negative number, which means this is undefined. So the solution is undefined for this one. Alright, what if we just did a general g of f of x? What if we're just plugging in our variable x? So we're taking g of, and then we just copy down f of x, which is the x squared minus 2, which is equal to 1 over the square root of, and then our input is that whole function x squared over x squared minus 2. Now, this right here is a complex number. I have a fraction within the fraction, and I don't want that. So I'm going to show you some tips for how to move this around so that we can simplify it. So what you can do with the square root is you can actually separate it across numerator and denominator down there, meaning that's the same thing as the square root of x squared over square root of x squared minus 2. That comes from some exponent properties that we learned back in algebra, that if you have this situation too, of if you have a square root across the numerator and denominator, you can create one big square root. But you can also work the reverse of separating it across the numerator and denominator. So then what we can do is exactly what we did up above there of multiply by this least common denominator, which really there's only that root x squared minus 2, and whatever we do to the denominator, we have to do to the numerator as well. So down below, we'll get this cancellation, which is perfect. That's exactly what we wanted. So in the numerator, 1 times that square root of x squared minus 2 over square root of x squared. And you could leave it like that, or if you want to go one step further, that's the same thing as the square root of, and you can have it all underneath. And then you could look at simplifying more. Really, you could leave it just like that. The only other kind of thing you could do is separate up this calculation here. Like you could take this to square root of x squared over x squared minus 2 over x squared. And then you could see how that would be a square root of 1 minus 2 over x squared. That would be another way to express the solution. It just kind of depends on how far you need to take it to simplify. But I would say these are similar in terms of simplification.